Alright, for this part of the video I want to talk a little bit about convergence. And the basic notion here is that as you reduce the element size, or as you refine your mesh, you should get more accurate solutions. And what is the order of convergence? How is the error going to scale as you refine your mesh? And this is important, and also important to know when is this not going to work. First of all, these rates of convergence that I'm going to give you work for cases where the material is not incompressible and the geometry doesn't have kinks or 90-degree corners or less. Then the solution should converge in the energy norm with the same degree as the polynomial approximation, and it will scale with the mesh size. The energy norm is basically is defined as this integral. So you have, it's sort of like the square of the strains or the square of the stresses. So in a way, you can think of this energy norm as measuring your error in the stresses. And so this energy norm will converge with degree p, where p is the degree of the polynomial that you're using for the shape functions. So if you have, and h is the mesh size. So if you have linear elements, then your error will decrease linearly as you refine your mesh. If you have quadratic elements, then your error will decrease quadratically as you refine the mesh. And again, this energy error is basically an error on the stresses. There's other types of errors. There's, for example, the displacement error. So the displacement you can get with more accuracy. So for example, if you have linear elements, the displacement is more accurate than the stresses. The displacement will converge with p plus 1 rate. And now this is true, again, if there is no singularities in your solution or no incompressibility. So if you have, the standard linear elasticity problem with a really nice and smooth domain with no corners, then you will get these orders of convergence. But this will not be the case if you have some problem with a singularity. And this is what I want to show here. For example, this is one problem that is nice. It's a smooth domain. There's no corners. So if you solve this problem with linear elements, you will get, I'm gonna guess that this is the displacement error. So you're gonna get quadratic convergence in the displacements using linear elements, and then you will get more convergence using quadratic, so higher rate of convergence, and then you will get more convergence with the cubic, right? So this will be, so as you refine the mesh, you get better and better in the solution. But this is true if the mesh, the geometry doesn't have any kinks. Now, what happens if you have very similar problem, very similar problem, but now you have this 90-degree corner, and that makes then you have a singularity here. So then now it doesn't matter whether you use linear, quadratic, or cubic or quartic elements. You just don't get better convergence. So in this case, you can see that because you have a singularity, then your convergence is linear. So it doesn't matter whether you use the quadratic elements. You won't get really anything out of it. So you just have to be very careful. This degree of convergence is dependent on the regularity of the solution, not just on the polynomials that you use for the elements. Another thing to note about convergence is that not all points have the same convergence. So if you think some points have better solution than others. For example, let's say that you are solving some problem with piecewise linear finite elements. And let's say that this is the exact solution. Then your approximation with the finite elements will look like this piecewise linear. The best point to evaluate the displacement solution will be at the nodes. So the displacement at the nodes is actually going to be very accurate, but then inside of the element is going to get less accurate. So the error inside of the element for the displacements is going to be bigger, but at the nodes is going to be the best. For the stresses, actually the error is worst at the nodes. So this is, for example, the exact solution of the gradient of the displacement. You can see that the gradient of the displacement, for example, for this problem, it changes linearly. And now your finite element solution, if you're using piecewise linear for the displacement, then the stress is piecewise constant. So you can see that for this element, the stress is this horizontal line. And for this second element, the stress is this line. So now you can see that for the stresses, the best point is at the middle of the element. So if you sample the stress here, you will get some value that is very close to the exact solution. Whereas if you try to evaluate the stress, for example, at the node and compare it to the solution, then you get a really big error. Actually, the worst case is if you try to compare the exact solution at the node with the stress of this element. So here, again, the best point will be the center of the element. And this is something that you have to keep in mind about where to sample your solution. For quadratics, similar thing. So these are quadratic elements. These are 3 quadratic elements. Every quadratic element has a node at the 2 nodes at the boundary of the element and an interior node. So for this element, there's 1 node here and 1 node at the end of the element and 1 interior node. For this element, again, there's 2 nodes at the boundary and 1 node inside of the element. And then for this element as well, these 2 nodes are on the boundary and then this is inside. And here, for example, the exact solution is this black line, and the quadratic approximation is this, with the finite element, is this dashed line. And here you can see that the best way to evaluate the displacement solution is at the exterior nodes. So in this case, you can see that at this point, so at the node, the finite element solution and the exact solution match. They also match at this node, right? And they also match here, and they also match here. So at the nodes that are in between the elements is where you get the best displacement approximation. Again, what happened with the stress? So for the stress, again, we have the same mesh here. This is the same element as you have here. This is the same element as you have here. This is the same element as you have here. And now the exact solution for the stress is this black line. And now, because you're using quadratic elements, then your finite element prediction for the gradient is going to be piecewise linear. So you can see now that inside of element 1, you get this line. This is the approximation for the gradient from the quadratic elements. Again, because they are quadratic elements, that means that the gradients are piecewise linear. So you get the first line is the gradient inside of element 1, then this line is the gradient inside of element 2, and then this last line is the gradient inside of element 3. And now you can see that where is the best location to evaluate the gradients. Well, it's not in the boundary of the element, but actually at the integration points. So you can see that somewhere, like a little bit inside of the element, in this location, you have an exact solution matching the finite element solution. Then at this point, again, you also have the optimal sampling point, because here the finite element approximation matches the exact solution, and this is again somewhere inside of the element. For element 2, again, the 2 points that are the best to evaluate are this white point here and this white point here, which are again somewhere inside of the element. And then for this last element, the best points are these 2 white points, so this one right here and this one right here. And again, these 2 points are going to be somewhere inside of the element. So the bottom line here is, for the displacements, the best point to evaluate are at the nodes. But for the stresses, actually, the best points to evaluate are inside of the element, and most of the times in the integration points. There's some tables that you can use. This is from the Sankovich and Taylor book that tell you what are the optimal superconvergent sampling points for different types of elements. Another example of, and this should look familiar to the lab that we did. I think this was um, lab 5, I want to say, the finite element selection. So here you have a cantilever beam with some load at the top, and then let's say we're interested in the shear stress with these quadratic elements. Um, the exact average shear stress is this black line. However, your interpolation from the finite element solution is this dashed line. So again, you can see that you can get really huge discrepancies between your solution predicted by the finite element and your exact solution at many places, but there's points where you actually will get the best. So here at these integration points, if you evaluate the stress at this point, then you will see that your finite element evaluation is exact with respect to, I mean, it's the same as the exact solution. So for this element, for example, evaluating at these 2 points is the best. For the second element here, evaluating at these 2 points is the best. For this element right here, evaluating at these 2 points is the best. And then for this one, again, at these 2 interior points is the best. And this is for the stresses. So again, for the stresses, the best location to evaluate is at the integration points. That's where you're going to get the best approximation to your solution. And I think that's all I have.